you, Mr. Wenger. Good morning to all of us, all of participants in today's MRT program. MRT is a regular program in our department every month. We thank God for this wonderful opportunity. I am Febri Odelnitbani, the head of chemistry department, Nusa Cendana University. I would like to express my great appreciation to all the participants and our special guest speaker today, Mr. Edward Naul, Ph.D. from the School of Chemistry, the University of Melbourne, Australia. Thank you for being a guest speaker in our MRT in August. Thank you to my colleagues who have prepared today's webinar. With God leading, I open today's MRT activity, and please join this program until the end. Thank you.
Thank you very much.
Thank you very much.
Professor
Thank you.
Febri. And now the talk will be chaired by David Tambaru. David will chair the talk. Edward, please keep slowly because talk slowly because some of us have to understand English. They have to double process of understanding.
Of course.
Okay, thank you. Time is yours, David.
Thank you so much, Barida. Today is our the first monthly research talk in this semester. So we are so honored to have Dr. Naul here with us to share his experience in the field of analytical chemistry. Especially in the field of phosphate and flow injection. So Dr. Naul completed his bachelor and master and his PhD at the University of Melbourne School of Chemistry, as I believe. He joined the University of Melbourne in 2018 for PhD, and then upon his PhD completion, he moved to a company, quality assurance or quality control companies. And there, I think he got a lot of experience as well. Maybe would be good to be shared a little bit maybe later on. And then after that, joined again to the University of Melbourne to do his postdoctoral fellowship. And I was blessed to have him at the same time when I was doing my PhD. And he has been the one who really helped me a lot to go through my PhD struggle. And today, I'm so happy and I think feel blessed again to have him here with us. And he's going to talk about the phosphate and the system, what we call flow injection system he developed to detect phosphate in environmental sample. So his work is mainly in analytical chemistry, chemical sensing, separation science, and polymer inclusion membrane. Also polymer nanostructure detection or analysis. So for the next 40 minutes, maybe, or 40 minutes, Dr. Naul will be sharing his expertise. So I hand it over to you, Dr. Naul.
Much appreciated, David. Now, just allow me to share my screen. That is the wrong screen. Just flip it. All right, is that coming through properly?
Yes.
Absolutely.
Excellent. All right, so the title of my talk today is Phosphate Determination in Water Using Flow Injection Analysis with UV Photoreduction. So a little bit about my background first. I've looked at a number of research questions in my work so far. The first one was, can we combine flow analysis and analytical chemistry with membrane science? Because in the laboratory that I've worked in, chemical analysis and membrane science have been two big research areas, and we use membranes for separating analytes from natural samples. The answer to that first question was yes, we can. This was in fact my master's project, where I designed a flow injection system for detecting phosphate using what's called a polymer inclusion membrane, essentially an ion exchange transporter. Another research question I faced was, how does phosphorus detection chemistry really work? There's been a method that's very commonly used in the literature for over a century, but there have been some misconceptions about how that method worked. And so I led an investigation of how that actually functions, which was really interesting. A third research question I've looked at was, with these polymer inclusion membranes, what do they actually look like on the inside? People have done all kinds of characterization of their function and the large-scale results they can give with separation, but no one ever really looked at what makes them work at the molecular level. So I used some X-ray scattering studies to work out what made those work. But for now, we're keeping the topic more to analytical chemistry.
Sorry,
So
sorry, but sorry for interrupting you. The picture, the screen share is not too clear to be looked.
Oh, is that?
I think something.
Yeah, that's small. Yeah.
Yeah, that's better, I think.
Okay. Oh, is it too squashed?
Maybe you can change to the how do you call it? One layer.
Page, just only one page. Because what we are looking here, there are two pages on the same time. So the one that you are talking is to.
Is that better now? Because I've just swapped them.
No,
No, the previous one is
back to
better.
Okay, apologies for that. Let me just tweak something on my end. And allow me to share this one. Is that any better, or is that a bit small?
It's quite
It's
still
better.
quite small, yeah, but we can see.
Okay.
Yeah.
Sorry, I have one more thing I can try. Let me just shift it to another monitor. I think this should work a little bit better. Sorry, PowerPoint is being a little bit uncooperative at the moment. Okay, so let's try that.
Yeah.
Yeah. Excellent.
Fantastic. Yeah.
Okay, sorry about those little glitches.
All good. All good.
Okay, so as an outline of my talk, I'm going to go through some background on orthophosphate and why measuring it in the environment is really important. I will then talk about the detection chemistry that's often used for that, especially the molybdenum blue reaction. Next, I'll talk about some molybdenum photochemistry because that underpins a lot of the work in this particular study. I'll then talk about the design of a flow injection system I'm using that actually exploited that photochemistry for phosphate detection. And then I'll finish off with the conclusions of the study. So this work is in fact published as a paper in Atlanta some years ago. And a lot of what I'm discussing comes straight from this paper with one or two little bits of extra information that we discovered after the paper was published. Isn't it always the way? So, as an introduction to orthophosphate, it is a primary nutrient. It is absolutely critical for all life. It's part of DNA after all. And when we look at especially algal growth and how important phosphate is for the growth of new life in general, there's this thing called the Redfield ratio in the literature, which is essentially the stoichiometry of what it takes to create an algal cell body. So this ratio says that we need about 106 molecules of carbon dioxide, 16 nitrate ions, over 100 water molecules, some acid, and 1 phosphate with a bit of UV light as well, which shows that this process is usually limited by phosphate. Therefore, in cases where we have excess amounts of phosphate, we can get huge amounts of algal growth, which can be really, really bad for the environment, because that leads to what's called eutrophication, where we get excessive amounts of algal blooming, which can have direct toxic consequences for people nearby. But also, once those algae inevitably die off, their decomposition consumes the dissolved oxygen in the water, which can lead to so-called dead zones. Now, eutrophication is a worldwide issue and usually comes about because of contamination of waterways from agricultural runoff, such as from fertilizers, sewage discharge, detergents, and also industrial waste streams. So monitoring of orthophosphate content in the environment is really important to identify these pollution events and, if possible, stop them before they get any worse. The two standard methods out there for detecting orthophosphate are both spectrophotometric. So they both use UV-Vis. The first one of those is the vanadium-molybdate method. So this one is quite simple by comparison. It is a single-step reaction where phosphate reacts with molybdenum-6 and a metavanadate ion, and that forms a molecular cage. And that is quite a bright yellow in color. The maximum absorption wavelength of this complex is about 315 nanometers. So whilst it's a quick, simple reaction to do, unfortunately, that absorbance wavelength means that if your sample has any kind of color at all from organic matter, it immediately becomes a problem. So organic matter tends to give samples a yellow or brown appearance, and that is going to directly overlap with the absorption of this compound here. In fact, in standard methods, pretty much the handbook of the typical methods used in industry to measure all kinds of analytes in the environment, they recommend using a much higher absorption wavelength to deal with this, but accordingly, the sensitivity becomes very, very low. So the alternate method is what's called the molybdenum blue method. Now, this one's a little bit more complex. Just like vanadium molybdate, we again form a molecular cage out of molybdenum and oxygen around the phosphate. But then there's a second step where we reduce that entire complex into a deep blue colored product. The chemistry of this is really interesting, and I published a review paper on it actually. The product you get is based on the reduction conditions you use. So a little bit more on that later. But it has the very useful benefit of absorbing at a much, much higher wavelength, between 700 to 880 nanometers, which means that generally speaking, unless you've got some really exotic trade wastes, the color of your sample is completely irrelevant. You can analyze whatever because nothing is really blue colored in the environment. It's also considerably more sensitive than the vanadium molybdate method. The molar absorptivity of the complex is about twice that of vanadium molybdate, and we don't need to move the absorption wavelength around because of sample color. So a little bit more on molybdenum blue. It is, by a long shot, the most widely used reaction for phosphate determination. Research, industry, environmental testing, wherever. Because of those advantages I mentioned before, it's unaffected by sample color. It's highly sensitive. You can get down to microgram per liter of phosphorus detection limits, and it's generally quite safe and straightforward to perform. And it is a two-step reaction, as mentioned before. And there's quite an interesting story in terms of the reaction conditions you can use. But the major issue with this reaction, despite its reliability, is that it needs a reductant, usually something like ascorbic acid. And the big problem with those is that they are inherently unstable in air, and they will react with dissolved oxygen in whichever aqueous medium you prepare them in. For example, with one variant of the molybdenum blue conditions, where you have tin 2 chloride and hydrazine sulfate as your reductant, you can actually monitor a consistent decay in the reaction sensitivity over 17 days, which means you need to recalibrate the method daily and or prepare fresh reductant daily. So this was a paper, I think, reporting the first ever flow injection analyzer using the molybdenum blue method, and they tracked the decrease in response over time. So it's been a persistent problem, and having to remake your reductant solution every day and recalibrate every day, sometimes more than once in a day, frankly, it's just painful. So the ultimate research question that I was facing here is there a better way of doing this? Because the reaction is otherwise so useful and so sensitive. Can we make it just that little bit easier to deal with? This is where we start talking about molybdenum's photochemistry, which was actually mentioned in an obscure Russian paper in 1969 and has been largely ignored ever since. This was first tested in the measurement of silicate, actually, where the authors used UV light and an organic acid to get reduction of that complex. So I thought, why not try the same thing here? Because as it turns out, UV light of about 220 nanometers will excite a molybdenum oxygen double bond. Because in molybdate polyanions, there are molybdenum oxygen single and double bonds. Now, upon irradiation and excitation of that bond, you turn that group into a very powerful and unstable oxidant. Which begs the question, what if we didn't need a conventional reductant at all? What if the power of that temporary oxidant means that we could use something else as our reductant, which is inherently stable? And it turns out you can do that. There's literature, in fact, on using hydrogen bond donors as reductants for this process, especially alcohols and amines. So the actual reaction mechanism is quite complex, and there's been a lot of investigation into that, but I can discuss that at the end if anyone's interested. But all you need for this is an H-bond donor and UV light, and boom, you have your reduction. Very quick, very clean. Now, there are significant practical advantages, in theory anyway, to using this approach. It means you can generate your reductant in situ, which means that your reagents are therefore stable for very long periods of time because you've just removed the unstable component. It would also mean you wouldn't need frequent recalibration. And furthermore, UV lamps are everywhere. They're very easy to obtain and usually pretty easy to integrate into whatever apparatus you're using. However, this interesting photochemistry has been largely ignored in analytical chemistry. Where it shows up in the literature, it's mostly used actually for water splitting, for solar energy storage, where it's got some interesting applications there. And I suspect a key reason that it doesn't show up in the analytical literature is because it's very awkward to do by hand. There's the obvious risk of UV exposure. There's the absorption of the UV by glassware, non-uniform irradiation. And there's also the fact that once you use this photoreduction process to create your molybdenum blue product, there's no reductant remaining in solution to keep it reduced. It decays very quickly. But the literature does agree on one thing, in that alcohols typically perform better than amines in other groups. So I thought, in this particular method, why not use one of the most common reagents anyone ever sees around a lab, and that's ethanol. It's everywhere. It's easy to get. So, as a test run of this chemistry, I decided to try irradiating the precursor to the molybdenum blue, and comparing that signal stability over time to a complex I prepared using a conventional reductant mixture with tin 2 chloride. Now, as you can see there, whilst the tin 2 chloride stays mostly stable over that time, there's always a little bit of decay. The UV product, it decays pretty quickly. So if you were doing this by hand, it would be utterly impractical. You'd have to get your measurements right down to the second. And by the time you could do it, you've lost most of your signal anyway. It turns out, actually, the kinetics of that product reoxidizing are first order in both the concentration of the phosphomolybdenum blue, the PMB, and the dissolved oxygen. So it goes down pretty fast. But whilst this is impractical for doing by hand, flow analysis is perfect for this, because it means that if you can do this in a controlled system where everything's irradiated for the same time, and you can transport the product to your detector quickly, then you may just have a means of using this properly. So moving on to the design of that flow system. The flow injection system I designed for this ended up being pretty simple, all things considered. It's 2 reagent streams propelled by pumps, and they meet at a confluence point where they mix in a mixing coil that is within a UV reactor. So stream R1 was simply water. That was the carrier stream. And it's into that stream that we can inject our phosphate-containing sample. R2, our second reagent line, contains all of the ethanol, the ammonium molybdate salt, and the sulfuric acid, all the reagents in one bottle. And I used a 4-meter long reactor coil to make sure there was enough time to actually mix and irradiate the sample properly. And for this, I used a 40-watt medium pressure mercury lamp. So not the most powerful lamp out there, but definitely capable of spitting out a few photons. Now, there were a number of factors to optimize in this system, and they each had their own unique effects on how things worked. Starting with the sulfuric acid concentration. Acid is a crucial component of this chemistry because molybdenum blue is dealing with essentially polyoxometallate chemistry in inorganic chemistry. You're dealing with the condensation of molybdenum species to form larger cage-type structures, and that requires acid to form. The acid also influences the redox chemistry. If you have too much, you suppress the entire process. All of your precursor compounds break down, and you shut down the redox chemistry as well. So your sensitivity really drops with too much acid. But with not enough, you actually get a very strong baseline signal forming because you have other molybdenum compounds being reduced, which prefer higher pHs. So the optimal sulfuric acid concentration here was about 0.2 molar, which is consistent with many other molybdenum blue methods. The ethanol concentration, as the sort of working concentration after both the streams were merged, had an optimal value at about 7.5% volume per volume. The ethanol, as effectively the reductant in this method, had significant effects on the sensitivity of the method, as you might expect, and also the baseline signal. Just like any other molybdenum blue method, if you have too much reductant, you tend to get a very strong baseline signal forming. But if you don't have enough, then the sensitivity of the method is compromised as well. So 7.5% was the ideal point there. The molybdenum 6 concentration had its optimal value at about 5 millimolar, which again is pretty standard. Again, this one affects both the baseline signal and the sensitivity. If you have too much, again, you get that annoying blue baseline species forming and not your actual desired product. But if you don't have enough, then the sensitivity of the method also drops away. The flow rate of the method had an optimal at about 2 mil per minute, and that largely affected the sampling rate. One of the really interesting things about this method was that it supported much higher flow rates than other molybdenum blue methods. In those, it often takes time for the reduction process to happen, sometimes on the order of minutes, But in this case, as soon as it passed through the UV reactor, it was pretty much instantaneous. The injection volume was another important parameter. As in any flow method, the more sample you inject, up to a certain point anyway, the more sensitivity you get because there's more sample in there. But of course, if you're injecting very large amounts of sample, then you're going to have very broad signal peaks, which will essentially overlap with each other if you inject too fast. So I went with the maximum of that range there, 500 microliters, which was again pretty standard. The final optimization parameter was the UV reactor coil length, which I varied between 2 and 5 meters. It had its optimal value at about 4 meters. And that affected quite a few things: the sampling rate, the sensitivity in terms of the mixing, and also something called the Schlieren effect, which I know is something David encountered in his work as well. The Schlieren effect is essentially an optical mirroring effect. If you have two solutions of different refractive index and you don't mix them fully, then you get this kind of streaking effect. It's like if you mix ethanol and water, and for those first few seconds, you see like this blurring effect at the interface between the two. That causes scattering of light, which, if you're talking about a spectrophotometric system here, actually gives you distorted peaks and sometimes an oscillating baseline as well. So the better mixed those solutions are, and the closer their refractive indices are, the less that becomes a problem. So after all of that, the analytical performance of the system looked like this. The limit of detection surpassed my expectations. It was down to 0.2 micrograms per liter of phosphorus. So the sensitivity was definitely very, very high. The linear range of this method, though, was a little bit shorter than most of the methods out there, 0.2 to 250 micrograms per liter, whereas you see most phosphate methods usually go up to about 1 milligram per liter. However, this method had the benefit of having a full response range, so a useful range up to 10 milligrams per liter of phosphorus, because of how the reductant works. The repeatability of this method was also, I thought, quite good. 0.64% relative standard deviation at 250 micrograms per liter phosphorus. And that only went up to about 3.8% if we're getting pretty close to the detection limit. The sampling rate was also very high. It took less than 1 minute for each sample injection. When analyzing reference standards, the accuracy tended to be a little bit of an underestimate, but only by a few percent. And in the last major parameter, silicate is traditionally a great enemy of phosphate methods because it tends to interfere at least a lot with the historical methods. But testing silicate here, there was no interference from it below at least 50 milligrams per liter, which was very encouraging. So I mentioned that dynamic response range before. Turns out if you use a quadratic calibration plot, you can see the entire thing here. So here are signal traces of the system at a variety of injected concentrations of phosphorus. So you can see that the signal actually curves off quite early, but it is still usable all the way up to 10 milligrams per liter of phosphorus. Now, remember back to when I was talking about the decay kinetics of the reduced product, and that they were first order in both the product concentration itself and the dissolved oxygen. I suspect that the reason the linear range tapered off so soon was because of that dependence. Again, once the irradiation finishes and the product's making its way to the detector, there's nothing to keep it in the reduced states. The more product there is, the faster it's going to decay, which is why the linear range tapers off sooner. So the next step was to test this system out on real water samples. So for this work, I took 5 water samples from a variety of water sources around Melbourne. Those were a swamp, 3 creeks, and the Yarra River, which is at times notorious for its cleanliness or lack thereof. Now, the point of interest here was one particular one, and that was in the UV absorbance of these samples. Thought process was, if the organic matter in these samples absorbs heavily around where our molybdenum oxygen excitation wavelength is, then are we stopping the UV light from actually exciting that and doing the reduction process? In short, will the UV absorbance of the samples directly interfere with the reduction? As it turns out, not so much. With the validation study I did, the spike recovery on most of these samples was actually excellent. With a number of the creek samples, it was very close to 100%. And in the most intensely absorbing sample, which was Bell's Swamp, the spike recovery actually gave a slight overestimate of phosphate, not an underestimate, as I expected. In fact, the lowest spike recovery of all was in the Yarra River, which actually had the cleanest UV-vis absorption spectrum of the whole lot. So there are obviously elements of these sample matrices which could still potentially interfere with the method, but not to a massive degree. So by and large, we can conclude the system does actually tolerate dissolved organic matter, or DOM for short. So particularly with that swamp sample, we found that the method did tend to overestimate phosphate content in some waters versus the reference molybdenum blue method. And that begged the question, why? In quite a number of literature methods for phosphate, especially the older ones, there's a lot of consideration given to whether or not the method is measuring phosphate from other sources as well. Normally, what we want is to measure just orthophosphate. But because of the acidity or the reaction time or even the use of heating, it is possible that in some of these methods, you can actually hydrolyze or oxidize phosphorus from other phosphorus sources in the environment. Those can be inorganic polyphosphates, which can be broken down generally by acid and heating, or you can have organophosphates, from which you can get orthophosphate by oxidation, especially if there are harsh conditions involved. So the question here is, this excess phosphorus we're seeing, where's it coming from? Is it oxidation or is it hydrolysis? So to answer that question, I looked at 3 model organophosphorus compounds: phosphocholine, glycerophosphate, and phytic acid. Now, just running acid hydrolysis experiments at that 0.21 molar sulfuric acid concentration yielded negligible hydrolysis. So we can be pretty sure that wasn't the source of the extra phosphorus. It turns out that the UV, though, was in fact the culprit, because there was a small amount of oxidation of these organic compounds when we actually put the thing through the UV reactor. Only between 2 to 4 mol%, but it was there. So in samples that are very high in organic matter, such as that swamp sample, it does then make sense that that small amount of oxidation gives us slightly higher recoveries than we would expect. But it wasn't nearly as bad as we potentially expected. Sorry, PowerPoint seems to have frozen on me. There we go. Now, the next matrix I looked at as well was seawater. Seawater, as some of you may well know, tends to be a pretty notorious sample matrix in analytical chemistry. It doesn't get along well with a lot of analytical methods. The matrix can be harmful to a lot of instruments, and in some cases, it can just wipe out or interfere with your chemistry very, very badly. However, it is a very important matrix to be able to analyze, especially when looking at trace phosphorus determination in the environment. Because phosphate in seawater is key for understanding the biogeochemical cycling of phosphorus in the environment and a lot of applications in climate change. Remember the Redfield ratio, how phosphate in seawater is the limiting reagent for algal growth. If that's the case, then carbon dioxide uptake from biota in the ocean is limited by the amount of phosphate that is in the oceans. So if we can characterize how much phosphate is in seawater at different parts of the globe, we can get a very good picture of how atmospheric CO2 and seawater can properly interact. Unfortunately, though, we have the twin problems of a very difficult matrix and very, very low concentrations of phosphate, usually in the low micrograms per litre range. So in this case, we again look at the absorption spectra. Is seawater going to potentially cause issues? It turns out that, again, seawater does absorb very strongly, in fact, around 220 nanometers, which sort of made a bit of a pit form in my stomach when I was looking at this, thinking, oh no, it's going to wipe out the method completely because it's going to absorb all of the UV. Because there was a distinct possibility of reduced photoreduction efficiency here. Mercury lamps emit most of their light at 254 nanometers. So 220, which is where the bond excitation for the reduction happens, isn't even at the peak of that emission. However, it turned out that the system actually tolerated that a lot better than was expected, probably because of the dilution of the sample in the overall system. Because looking at phosphate spiked into seawater, there was only a 15% decrease in the calibration slope. So the sensitivity was still definitely usable, and the system itself would remain applicable to seawater samples if the salinity remains more or less consistent. So we would only really expect to run into issues in estuarine samples, for instance, where salinity can be quite high and extremely variable. But otherwise, for fresh waters and for seawater, the system definitely seems to have gone through its paces and survived them quite well. Now, there was one part of this study which didn't make it into the paper because we only discovered this after the paper itself was published. We used methanol as the photoreductant in this, we used ethanol as the photoreductant in that paper. But there were, even after publication, still some issues with the signal baseline. It was oscillating. It was forming these sort of wavy patterns which simply would not go away no matter how much I tried to mix the sample. And again, that had one obvious cause, which was the Schlieren effect. So we wondered, what happens then if we try and find a photoreductant that has a refractive index closer to that of water? I've got the refractive indices of water, methanol, and ethanol in the bottom right here. So we can actually see that the index of methanol at standard conditions is actually very, very close to water, whereas ethanol is a little bit further away. So I substituted ethanol for methanol in the entire system and got pretty much the same sensitivity, which was fantastic, and also reduced the baseline noise substantially, which was the end goal. So that was a real improvement on the system. However, there was something interesting going on in the spectra here. As I was optimizing the methanol concentration, it turned out that the absorption peak of the overall product we formed tended to move around a bit depending on what concentration of methanol was used. Now, this was quite interesting because in looking through the literature on how the molybdenum blue reaction works, the typical species you form has 4 protons on it. It's still a highly charged anion, but it usually comes under standard conditions with 4 protons attached. It turns out that if you have that compound in organic media, you strengthen its acidity. So the more organic solvent you have, the more likely it is to deprotonate further. However, in the case of this method here, that's also unfortunate because the more highly deprotonated species give us more weakly absorbing products, which is bad for the method's sensitivity. You can see here actually that in the blue signal traces, as we increase the working methanol concentration from 2.8 to 3 to 5.2%, the peak shifts further to higher wavelengths and the maximum peak height drops in every case. Conversely, with the orange signal trace here, where we're using only 1.6% methanol, the peak height is actually lower than what we would get using 2.2, which was the optimal value. So in this case, it was a delicate trade-off between having enough of the alcohol to get virtually complete photoreduction, but not using too much so that we actually form a less sensitive product. So this brings us to the conclusions of that study. The goal was to develop a molybdenum blue system for phosphate detection, preferably at trace levels, that didn't need to use conventional reducing agents like ascorbic acid or tin chloride, and to therefore simplify the system and dramatically increase the robustness and reduce the cost. The outcomes there were that we could use UV light by exciting a molybdenum oxygen double bond and ethanol or methanol to reduce 12-molybdophosphoric acid to that molybdenum blue compound. The overall system used only a single combined reagent solution, which you don't see for other molybdenum blue methods, and that was stable for at least 3 months, and probably would have been for longer if I'd had time in the lab before publication. The method was highly sensitive and reproducible, able to go below 1 microgram per litre of phosphorus, and it was surprisingly tolerant of organic matter and seawater. And just showing the graphical abstract again of the overall flow chemistry and the flow injection system itself. So after all that, I'd like to thankfully acknowledge Professor Spaz Kolev, who was my supervisor at the time, Dr. Ian McKelvey, my sage counsel for a lot of this, especially on the environmental chemistry and detection of phosphorus, the Kolev group in general, David for his kind invitation to speak today, and all of you as my audience. I'm more than happy to answer any kind of questions you may have about any of this or the chemistry. There are plenty more details we can go into if anyone's interested. Thank you very much.
Thank you so much, Eddie, for the great talk. So I hope we all have a little bit of insight about flow injection and phosphate in general. And then now we are going to the question and answer session. And I think I already saw 2 or 3 questions in the chat box. So if you, if you have any question, you can also raise your hand. And in the meantime, probably I will hand it over to Eddie again to answer those questions on the chat box.
Okay.
Do you see the question?
Yes.
See?
So,
yeah, maybe we start from Pak Rainer question first.
Sure. So could the conventional phosphate colorimetric UV visible based method be run through the typical flow analysis instead of using the rare molybdenum metal? So was that referring to the vanadium-molybdate method? Because typically when you look at phosphate methods, they all use molybdenum-6 in fact. And generally speaking, even though it is a transition metal, it's actually a comparatively inexpensive reagent, which is one of the key reasons why I think this reaction is used so widely across the globe. So, I mean, there are lots of phosphate detection methods that have been done in flow injection format, but the vast majority of them still use derivatization of the phosphate with molybdenum compounds. There are some, for example, which bind the phosphate to the molybdate and then use an ion pairing reagent, which is also a dye. And you can therefore measure the color intensity of that dye. Or you can use the vanadium molybdate, which is just a direct reaction, and you go from there, or molybdenum blue, where you've got the redox chemistry involved. Answering the accuracy question. So that minus 6.5% came from the system's response to a known reference standard. So a standard reference material that we purchased. So the actual phosphate recovery from that particular sample was 6.5% below what the stated value was. So it was a slight underestimate. All right, a couple of hands raised. Fidel.
Go ahead, Fidel.
I think you're muted. I still can't hear you, I'm afraid.
We can't hear you.
Still mute, but we don't.
No, muted,
Maybe-
but we
Or
can't hear.
maybe in the meantime, I could answer Marissa's
Yeah,
question.
Marisa question. Yeah, Marisa is from the University of Melbourne as well.
Oh, right.
She did his master, her master there, but now it's in
Hi,
UK.
Edward.
Hi,
Hi, Edward. Really nice talk.
thank you.
I'm no analyst of chemistry, so forgive me if my question probably sound basic or something like that. But I'm just wondering on your validation method about the spike recovery.
Mhm.
You chose 3 different compounds. Like I'm wondering why. Is there any specific reasons for those 3 being chosen? What's so special about them?
Hello.
Thank you.
All right. So these were considered representative organophosphate compounds in the literature. And when I say organophosphates, I'm not meaning sort of pesticides and that sort of thing. These are typical compounds that we see from just inorganic matter in general, phytic acid being a particular one. They also differ in their degree of how refractory they are. So how difficult it is to actually break the phosphate off and liberate it as orthophosphate, which you can then detect. So these 3 were essentially considered by the broader literature as good examples of what phosphate compounds you might see out there in your organic matter. Okay,
Right.
sounded like you had your sound back, Fidel.
Am I audible now?
Yes, there we go.
Okay, thank you. Thank you. Well, thank you for briefing second amazing talk. As always, Eddie.
Thanks.
Well, it's been a while since I left the lab, but I can hear such an outstanding talk, Eddie.
Oh,
Well,
thank you.
getting back to the linear range.
Yes.
Can we still use the quadratic equation, or did you work out all the characteristic using the linear range only?
So the standards and the spikes and all that sort of thing, those were all done within the linear range itself. And that is, broadly speaking, where you would normally look for with a phosphate method. Unless in most applications of it, you're either characterizing trace levels and reporting what those are, or you're an environmental testing lab looking for where the phosphate is over the regulatory limit, or if there's been some kind of pollution event. So it tends to be either very low or very high concentrations you're looking at. So for the sample spikes and such, that was all within the linear range in that sub 250 microgram per liter range. But you could absolutely use the quadratic equation to look at higher phosphate concentrations. Perhaps in some cases, like clinical samples maybe, which is where vanadium-molybdate has often been used actually because of its ease of use and where its lower sensitivity is generally not so much of an issue. So yeah, I would advise against using the quadratic equation for very low concentrations, simply because of how least squares fitting works. It tends to bias toward the higher concentrations, so the fit isn't as good at the lower end.
Thanks, Eddie.
No worries.
Thanks, Eddie. Any more questions? I have a question. So my question is related to your experience in the company.
Yes.
So it must be a very rich experience. So can you share with us a little bit of the challenge or the opportunity or something else that important related to our field in analytical chemistry? Thank you.
Absolutely. So I worked at a company called Eurofins Environment Testing Australia. So Eurofins is a multinational, very large company looking at not only environmental analysis, but various other kinds of analysis as well. They now do microplastics testing, they look at asbestos testing, all kinds of things. So for the first 6 months I spent there, right after finishing my PhD, I worked as essentially an R&D chemist. My main project there was actually developing a total organofluorine detection method, because at that time, PFAS, which I'm sure just about everyone's heard of, were a very, very big thing, which the company wanted to sort of put to market as well. Because in a number of cases, if people have the mass spectrometry equipment required, you can analyze for particular PFAS compounds, but they wanted a secondary sort of catch-all method where you essentially pyrolyze your sample and look at all of the fluorine coming out of it. So in that case, I actually used combustion ion chromatography to do total fluorine determination in samples. After that little stint, I became the assistant technical manager for that company in the Australia and New Zealand region. So a lot of that work revolved around modernizing and redeveloping a lot of their chemical detection methods and coordinating the development of those methods between the different labs. Because a lot of them specialized in certain things, but not others. Some of them did things a certain way, whereas others would have a particular way of doing it differently. And making sure that all of the procedures in those labs were still up to NATA accreditation. NATA is the National Association of Testing Agencies in Australia. It's their accreditation and their stamp of approval, which any kind of testing body needs before clients will go to them. It's essentially the accreditation that says, yep, you're doing the standard method and it's up to our standards. A particularly interesting thing I found there was that the vast majority of the methods used were all from standard methods in water and wastewater. Now that's a reference text which hasn't been updated for about 20 years. Because as you might imagine, in an industry where compliance is priority one, change does not happen quickly. And if you're looking at validating new methods, those normally need to go through quite an exercise to actually get them approved and recognized. You need to send out the same samples to a great number of laboratories pretty much simultaneously. You've got to make sure the samples aren't too old by the time they get analyzed. You've got to collate everyone's results, keep in mind the fact they're using different methods, and then analyze the performance. So even though it was heavily regulatory bound, there were a number of instances where there were a lot of improvements that could be made, both in terms of efficiency and also in terms of OH&S. For example, in the phosphate with the molybdenum blue, there were tweaks that could be made. And again, they used a flow injection analyzer in an environmental testing lab, just like I had in the research lab. There were tweaks which could be made to improve sensitivity in certain cases where required. And for example, with their, again, flow injection methods for nitrogen detection, for instance, it was possible to actually make the method a little bit friendlier and safer by doing a quick substitution of reagents, whilst still having the method technically be validated and having the same performance as the original. There is a big push in those kinds of labs to actually automate a lot of chemistry which was once done by hand. A lot of those go to both flow instruments and also discrete analyzers now. So there's a lot of emphasis on now just miniaturizing it, decreasing the volumes as much as you can, and just going boom, 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 getting as many samples out in as short a time as possible. So it's a very, very different environment to a research lab, but it was really useful perspective.
All right.
I might just add there as well quickly, some of the other work I did was looking at some prototype technology for microplastics detection, which is also quite a big issue nowadays too. And that was using a rather special, still prototype instrument, using what's called LDIR, laser direct infrared, where you can actually take infrared spectra across an entire plane with your microplastic samples on there and then match those to a library. So really interesting.
All right. Thank you, Eddie. I believe there are a lot of things to say about your experience, but unfortunately we're running out of our time. So I think I will finish there. And I think Pak Rainer is raising his hand. Do you want to say something, Pak Rainer?
Yeah, it's quite interesting to know whether the byproducts that you produce over the molybdenum ethanol oxidation. You got a acetaldehyde as the byproduct.
Yes.
Any idea of doing something further of the byproducts?
So I would imagine those would be in fairly low concentrations, and the reductant could always be tweaked if the toxicity of the byproduct is of concern. For instance, if you use methanol as the reductant, then you would get formaldehyde coming out, which also isn't great. But for instance, if you were to use propanol, then you might get the 3-carbon equivalent of that, or for instance, amines. There are a variety of things you could possibly use, and you could always tweak it to the use case. Because if the efficiency of the reductant is a bit lower, you could potentially then use a stronger UV lamp, for instance.
No, I mean, maybe it could be the idea of scaling up of the methods of transforming the ethanol using the molybdenum to produce the acetaldehyde in the bulk process, might be something like
yes, absolutely. That's definitely an interesting potential application, which is actually a lot closer to the photochemical applications of this I've seen in the literature.
Yeah.
Okay. So I'm not surprised because Farina is a synthetic person, so he's
right, because you actually see 12-molybdophosphoric acid, 12 MPa, used a lot as a catalyst in the literature for lots of things too. So it's a really interesting prospects.
Okay.
All right, thank you so much. Yeah, I think we are running out of time already. It's past already.
Thank you, Eddie. And I think our dean is already here, and time is for Professor Phillips to close the
closing remarks.
Yeah, to close the occasion, Philip.
I guess he left already. I think he has something to do again. So maybe
that's okay.
We just close it here.
Okay. Thank you very much, Eddie.
My pleasure.
Nice to have you for this occasion, and thank you for all the participants. And I think any photo session before.
Our dean is there. Apparently, sorry, our dean is here again.
Sorry?
Yeah, I think I see Philip.
Oh, Philip. Yeah. Philip?
Philip, can you say something as a closing remarks for us? Are you there?
Also, for one interesting point is Marisa, the people, the one who asked you before, Eddie, she is in UK in the midnight right now.
Oh.
Joining the MRT talk just to hear from you.
I appreciate the dedication.
Yeah, it's around 2 a.m. here. I'm still awake, so it's fine.
The things we do for science.
Yeah.
Prof. Tony, something to say?
Well, I think that's a very, that's a very huge significant information for me. Yeah, this is what I really see, that how you validate the method and then repeatability. Everything was so great. So thank you for your. Yeah, I mean, this is like one that I should follow for next developing some method again.
Much appreciated.
Right. So I think that's enough for today talk. Thank you very much, Eddie, and all the participants. Thank you, and see you on the next MRT next month.
Thank you.
Thank you very much.
Thank you, Eddie. Thank you.
My pleasure. Thank
Bye.
you.
Bye. Ini lanjut. Stop ya.